All right, so I want to derive the formulas for the capacitance of a parallel plate capacitor, a spherical capacitor, and a cylindrical capacitor. Now you might be like, derive the formulas for? Man, I already know the formula for capacitance. It's charge per voltage. And that's true. This is the definition of capacitance. And this is always going to be the definition of capacitance. But when you deploy this definition against, say, a parallel plate capacitor, how does this ratio of charge per volts change if you vary the distance between the plates or the area of the plates? Similarly, if you change the radii of these spheres, does that change what the ratio of charge per voltage will be for this system? The answer is yes, it does. We're going to derive formulas that show us how these physical geometrical characteristics change what this ratio will be. So let's start with the easiest one. We'll start with the parallel plate capacitor. Let's say you got two plates and they have areas A and they're separated by a distance D. So we want to know how much charge per voltage will there be. So parallel plates are nice because if you remember from Gauss's law, if you throw some charge on here, so we'll have positive charge, let's say on the top plate, and negative charge on the bottom plate, you should have equal and opposite charge on each plate. So this would have positive Q and this would have negative Q down here, spread evenly. If you have a plate that is large, if you remember from Gauss's law, it creates an electric field that is uniform. That is to say, the electric field that comes out of the positive and goes toward the negative will be the same everywhere in space, which is kind of weird. It doesn't get any bigger or smaller as you move from the positive plate to the negative plate. The electric field maintains the same value. This was freaky. The infinite plane creates an electric field that does not depend on how far away you are. So that's why this one's kind of easy. The electric field in here from an infinite plane, see if you remember, is sigma over 2 epsilon naught. But we've got two plates here. So the positive plate creates a field down because out of the positive. The negative plate also creates a field down because it goes into the negative. So this was the field from one plane, infinite plane. So the field from two of them would be 2 times this, or in other words, the electric field in this region between two capacitor plates is sigma over epsilon naught. Again, that just comes from Gauss's law. And you might be like, wait just a minute. This is not an infinite plane. It can't be. Like, this capacitor's got to fit in your computer or your car, and your car's not infinite, so how could this be an infinite plane? All right, so it isn't. This is not an infinite plane. This is going to be an approximation. What you want to do, for this to be a good approximation, you want this distance here to be small relative to the other dimensions. That is to say, if the sides of your parallel plate capacitor are large compared to this distance between the plates, then it's a pretty good approximation. This is effectively infinite compared to the distance between the plates. You start making this distance too big, this is going to be a bad approximation. Also, there's edge effects we're going to neglect. The electric field's going to start bowing out over here, and we're neglecting all these edge effects, but they're insignificant if you make these plates really close to each other. And, I mean, you still might not buy that. You're like, so you're telling me it's wrong. And I'm like, yeah, not true, but let's say you're going to be accurate to the 7th digit. Your equipment probably isn't even going to measure to the 7th digit, so no one's going to know. So what's the difference is what I'm saying. So this is the electric field in between there, except you'll notice in our capacitance formula, there's no electric field in here. What we have is voltage. So what we need to do, the way you derive these formulas is you take your electric field, you figure out what that is. Then you turn that into a voltage. So how do you use electric field and turn that into voltage? You use the relationship between voltage and electric field, which says delta V equals negative integral of E dot dr. And we'll go from one spot to another spot. So I'll just go from say the top of this plate to the bottom of this plate. And I'll call the top 0. No, we'll go from the bottom to the top. It'll make more sense. So there's no like double negative here. From the bottom to the top, we'll go from 0, call this height y equals 0, all the way to y equals d. So we're integrating from the bottom plate to the top plate, the e along that direction. What are we going to get? We get negative the integral, 0 to d. Let's see, e is technically pointing down, and if we're defining up as positive, because we went from 0 to d, Then I got to plug this in as negative sigma over epsilon naught is my electric field. And then dr, but dr really is just dy here, like my direction I'm integrating is in the y direction. So if I do that integral, negative cancels negative, I get sigma over epsilon naught. Integral of dy is just y, and if I go from 0 to d, I just get d. So this is what the delta V is if I go from the bottom plate to the top plate. Notice it came out positive, which makes sense. If we go against the direction of the electric field always points downhill toward lower V. Now if we integrate this direction, we're going uphill, so my delta V came out positive. I ended up at a higher V value than where I started. This bottom plate is at a lower V value than this upper plate is. So after you find your delta V, the next step is to plug it into your capacitance formula. So let's try it out and see what we get. Capacitance of a parallel plate capacitor is going to be the amount of charge we put on the plate. And then we divide by delta V. Well, I found delta V. Delta V is this. It's sigma over epsilon naught times d. And you might be like, well, that's kind of ugly and dumb, but we can simplify this because sigma is the charge per area. So I can write this as Q divided by sigma, which is charge, the amount of charge on the plate per area. And then I'm having 1 over epsilon naught. So I'm going to bring that epsilon naught up top. And then I also have this d sitting here. So we can cancel off the q's. Q cancels q, and you notice I also have 1 over the area. So what I get is that the capacitance of a parallel plate capacitor is going to be epsilon naught times the area over the distance between the plates. This is the formula for how the capacitance of a parallel plate capacitor depends on its area and the distance between the plates. So this makes sense. The bigger the area, the more it's going to be able to store charge. So the larger this capacitance number. This parallel plate capacitor will have more ability to store charge. Its capacitance will be larger if it has more area. And then the smaller the distance, the closer you put these plates together, the larger the capacitance is going to be. And then it depends on this permittivity of free space. The only way you get a different number here is if you plug in a dielectric. So if you stick a dielectric in here with some dielectric constant kappa, so you can change what this permittivity is in this region between the plates if you put in a dielectric in here. That just changes E. You go from epsilon naught to kappa epsilon naught. So the only difference would be if you got a problem or a situation where you put in a dielectric constant, you'd have to multiply by that dielectric constant here. Okay, so recapping really quick, we found the electric field in the region between our plates. We turned that into a voltage. Once we had our voltage, we took that, plugged it back into the definition, and then canceled the Q's, and we get a formula based just on geometrical properties of the system. So let's try the spherical capacitor. So name of the game, first thing we got to do is figure out what the electric field is in here. This one's kind of easy. If we throw some charge, let's throw positives here, and we'll have negatives on the outside sphere. So this is a sphere inside of a sphere. How is it just levitating there? I don't know. These problems never tell you how this works. Maybe it's supported by very thin insulating wires or something. And they never really tell you because you're not going to really build a spherical capacitor, I doubt. This is probably the least practical of all the capacitors. But it's good for just showing how this works theoretically. So let's say you have positive Q on the inside sphere, negative Q on the outside sphere. So first things first, we need to figure out what the electric field is in this region here. It's not going to be uniform this time. The electric field around a sphere is not uniform. It gets smaller and smaller the farther out you go. Now, if you remember, the electric field from a uniformly spherically symmetrical sphere is just the same as the electric field from a point charge if you're outside of that point charge. So it's K, or you could use the fancy version 1 over 4 pi epsilon naught, or you could use K. This is the electric constant out here. K times Q over R squared is the electric field in this region between the spheres. Again, you can derive that using Gauss's law. So now that we have this, we have to get a voltage, because the voltage is in the definition of capacitance. And we find voltage the same way we always find voltage. Equals negative the integral from, let's just go from A to B This time we're going downhill. We're going to get a negative quantity out because I'm starting at the positive end. I'm going to end at the negative end. So I'm going to go from A to B, and I have this entire quantity here, this electric field, which is 1 over 4 pi epsilon naught Q over R squared, and then dr. Notice I'm going to integrate in the R direction, which is radially outward, and that is the direction the electric field points. So I'm plugging this quantity in as positive because it does point positively radially outward. So now I do my integral. I'm going to get that the voltage is going to be negative. I get all this constant stuff out. I can pull all the constants out. Q, I can pull out 4 pi epsilon naught. What I end up with is the integral from A to B of 1 over R squared dr. And so the integral of 1 over R squared is going to be negative 1 over R. So I'm going to get equals negative of another negative that pops out of there, so that's going to be positive, Q 4 pi epsilon naught, and then I get 1 over R evaluated between A and B, and so this is just going to be Q over 4 pi epsilon naught, and then I get the quantity 1 over B minus 1 over A, and you might be like, hey, you said this was going to be negative, this looks positive. Looks like it's a positive value out here. Well, look at this bracket term. 1 over B minus 1 over A is going to be a negative quantity because B is bigger than A by definition here. B is my outer radius. So 1 over a big number minus 1 over a small number is really a small number minus a big number. It's going to give me a negative number. My delta V came out negative. That actually makes sense. We went from the positive plate to the negative plate. Or in other words, we went in the direction the electric field was pointing, and the electric field always points downhill toward lower V. So we went from a high V to a low V, we got a negative number. This delta V in here is always just supposed to be the magnitude. So is this charge here, so it's good to say magnitude of the charge on one of the plates, magnitude of the voltage between the plates. So I just want to take the magnitude of this delta V. So I'm actually going to say that delta V is going to be, I'm just going to swap these so I get a positive number. I'm going to call this Q over 4 pi epsilon naught, and I'm going to say this is 1 over A minus 1 over B, at least that's the magnitude of what V is, or delta V between these spheres. So we used E to get the delta V. We take our delta V, we plug it into the C, and so we get the capacitance of a spherical capacitor is going to be Q divided by, and we get Q over 4 pi epsilon naught times the quantity 1 over A minus 1 over B. Or in other words, we can cancel off the Q's, and I get that C is going to be 4 pi epsilon naught over 1 over A minus 1 over B. And so this is how the geometrical properties, the radii of spheres, could change the capacitance of this system here. And again, we followed the same route. We figured out what the electric field is. We turned that into a voltage. We plug it into the capacitor formula, and we get what the capacitance is. So let's do one more. Let's do the cylindrical capacitor. So if you remember, the electric field from a cylinder using Gauss's law was lambda over 2 pi r epsilon naught. Again, use Gauss's law in cylindrical form here, and you get what the electric field is here. So let's say we had a positive charge on the inside cylinder and a negative charge on the outside cylinder. That would mean the electric field points again radially outward in here from the inside cylinder to the outside cylinder. So this is the formula for the electric field from a cylinder. Again, do Gauss's law if you forget what that was. We've got that. We're going to take this now and turn it into a voltage. We got to figure out what is the voltage between these two cylinders. That's going to be negative the integral from the inside to the outside. Let's again go from inside to outside. So I'm going to go from A to B of this quantity, lambda over 2 pi r epsilon naught, and then dr. So I'm going to pull everything out. I get delta V, pull my constants out, is negative lambda over 2 pi epsilon naught. And then I have the integral from A to B of 1 over r dr. Now the integral of 1 over r is just log of r. So this whole mess is just going to be negative lambda 2 pi epsilon naught log of b over a. Now again, I got a negative number here. Negative because I went from the positive charge to the negative charge. I went from high V to low V. That means my delta V came out negative. That's okay. I just want the magnitude of this thing, so I'm just going to make this positive. Log of B over A is a positive number because B is bigger than A, so log of B over A is going to be positive. Everything's cool here. I just want the magnitude of it. I take it, I plug it into here. I'm going to get that my capacitance is the charge divided by, I get lambda over 2 pi epsilon naught log of B over A. And you might be like, wait, I can't cancel anything here. You can though, because remember lambda is the charge per length. So if we think of this direction here as the length of the cylinder, what lambda represents is how much charge per length there is on that inside cylinder. So I could rewrite this as C equals, I'm going to bring the 1 over stuff to the top. I'm going to call this 2 pi epsilon naught, and then I have this Q that was already sitting up top. Then I have lambda at the bottom, so I'm going to replace this lambda here with the definition of lambda, which is charge per the length of the cylinder. And then I still have log of B over A. And so now I can cancel. I can cancel my Q, cancel my Q. My L is going to come up top, and I get that the capacitance of a cylindrical capacitor, based on its geometrical properties, is 2 pi epsilon naught L over log of B over A. And so this is the capacitance of a cylindrical capacitor. Notice, the longer it is, the more capacitance it has, and that makes sense. I mean, there's more surface area to spread that charge over if you have a longer capacitor. So sometimes people leave off the L here. They divide both sides by L, and they're like, okay, the charge per length of a cylindrical capacitor is this.